Hello guys, in this lecture we'll be talking about signed and unsigned operations in 8051 using Keil UVision 5. We'll be talking about signed operations, the overflow problem in signed operations, unsigned 8-bit operands, and some additional examples in Keil UVision 5, such as addition, subtraction, multiplication, and division of unsigned numbers, as well as addition of signed numbers. So this is the program status word register of 8051, where there are 8 bits in total, starting from D0 to D7. The first bit is the parity flag, then comes the overflow flag, then bank select registers, which are used for selecting the banks, then general purpose flag, auxiliary carry flag, and carry flag itself. So what are signed 8-bit operands? So the thing which we should keep in mind while performing signed bit operations are the D7 bit indicates whether the number would be positive or negative, and the remaining bits from D0 to D6 indicates the magnitude of the number. Suppose if my D7 is 0, this means that my operand is positive, and if my D7 is 1, operand is negative. So positive numbers are represented in the range of 0 to plus 127. And suppose if the positive number is greater than plus 127, this means that 16-bit operand must be used. But as you know that 8051 is 8-bit microcontroller, which means that it could process 8 bits of instructions at a time. It does not support 16-bit instructions. And for negative numbers, D7 bit must be 1, and magnitude is 2's complement of the bits from D0 to D6. So first we write magnitude in the form of 8-bit array, then we invert each bit and add 1 to it. This is the process of finding out 2's complement. Yeah. Overflow problem in signed bits. So we know CPU works on the binary system. That is, it understands only zeros and ones. And if result of an operation such as addition, subtraction, multiplication is too large, an error called overflow occurs. So let us know when is the overflow flag is set. So overflow flag is set to 1 if there is carry from D7 out, but no carry from D6 to D7. This is the first condition. And the second condition is that in signed number addition, remember only in signed number addition, if overflow flag is 1, result is erroneous, and if overflow flag is 0, result is valid. So as we observed in the previous this PSW register, you can see the structure, and here we have a table which states that the carry flag is set only when there is a carry from D7 bit. So there should be a carry out from this B. The auxiliary carry flag is set to 1 only if there is a carry from D3 to D4. F0 bit is used for general purpose. These 2 bits are used for register bank selection. There are 4 banks in 8051, and accordingly by setting these 2 bits we could select a bank. The overflow flag is set whenever the result of signed bit operation is too large and it causes higher bit to overflow. The parity flag is used to check errors or debug. So for odd numbers, number of ones p equal to 1. For even ones, p equal to 0. Yeah. In unsigned 8-bit operations, no bits are set aside for positive and negative numbers, just like as there was in signed 8-bit operations. Here the range is from 0 to 255, that is 0 to FFH and hex, and the carry bit is usually observed, and we need to check if it is setting or not, and 2's complement is performed. We'll be seeing examples of each one of these in Keil. So now let us see an example of addition of unsigned number. Here is the assembly code for this end, which begins from an instruction called org, which is a directive and indicates that the program has been started. So org 0000h here stands for hex. Then there is an instruction called move, wherein we move the content 0f5h to accumulator register. So there are various registers in 8051, and accumulator is used to store the bits and obtain the results of the operations. Then next we would add a comma 0bh as 0bh. This means that we transferred. This means that 0b should be added should be added to instruction which is present in A, that is F5. So now finally accumulator will contain the resultant of these both operands, that is addition between F5 and OB. Now let us see how could we perform the same without using any program. So in the previous slides we see that there are total 8 bits, D0, D1, D2, D3, D4, D5, D6, D7. Now let us split these 2 characters in 4 bits. So how can we write F in terms of binary? 1 1 1 1. And how can we write 5? 0 1 0 1. Yeah. Similarly 0p. 0 can be written in the form of 0 0 0 0, and B can be written in the form of 1 0 1 1. So a simple way to remember that is that just add the places where 1 is occurring. For example, this position, rightmost position stands for 0 for 1. Then this stands for 2. Then this is 4, and this is 8. It has a value of 8. So we need to make a 5 out of 4 binary digits. And how could we do that? So this is 1 plus 4. 1 to 4. Yeah. So 1 plus 4 is 5. And similarly, you could do all the others. Now let us see how could we add those. 1 plus 1 is 0 with carry 1. Again, 1 plus 1 is 0 with carry 1. And again, 1 plus 1 0 with carry 1. 1 plus 1 0 with carry 1. 1 plus 1 0 with carry 1. And similarly, here also 1 plus 1 0, and here there will be an additional carry. I forgot to write 1 here, but there would also be a 1 here as well. So as you can see, the answer here, that is from D0 to D7, is 0 0. That is why finally our accumulator register would have 0 0. There is a carry out from here, 1 plus 1 0 with carry 1. There would be a carry out from D7 bit. So C equal to 1. Now for parity, we could check the number of zeros. So as you can see, the number of zeros are even. 1, 2, 3, 4, 5, 6, 7, 8. Which is an even number. Therefore parity register would be 0. Auxiliary carry. Now let us see if we have a carry from D3 to D4. So here 1 plus 1 0 with carry 1. There is a carry from D3 to D4. That is why our auxiliary carry would be 1. I'll tell you how to perform the same using Keil UVision 5. So I'll tell you from scratch. Go to project, UVision project, give a name, signed, it's signed operations. Save. Go to legacy device database and search for Intel and 8051EH. Yes. Okay. Copy startup file. No. Then go to target one, source group one, right click and select add new item to source group one. Go to ASM file. Give it a name. Here I'm writing my code. Yes. Now we'll go to add, right click and do build target. Or we could also press F7. So here we can say that we have 0 errors and 0 warnings. That means we are ready to go and debug. Click on debug. And now here we can see the step and see the output change. So I would step one line. You can see in accumulator register F5 got stored. Next I added 0B to accumulator. So the result accumulator got changed to 00 and the PSW register got a value of 0xC0. You could also see the contents of the whole PSW register. My auxiliary carry was 1 and carry flag was 1 and all others were 0. So let's check. Auxiliary carry was 1 and carry was 0, which is the same. This means we could say that our program executed successfully. Now let us see how subtraction of unsigned numbers is performed. We use a command called subtract borrow, in which we take 2's complement of one number and add it to the original number. So for 2's complement, we need to invert the number and add 1 to it. So let us see what we are doing here. Yeah, we are first making carry 0, and then we are moving accumulator 3fh into accumulator and 23h into register R3. Then we want to subtract 23h from 3fh. So we use subtract with borrow a, R3. We first write 23 in the form of binary numbers. So this is 2, this is 3. We then invert the bits, making 1 to 0 and 0 to 1. So 1 is converted to 0 and 0 is converted to 1. Then we add 1 to it. So we add 1 and perform addition. 0 plus 1, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, and likewise. Going forward, this is our 2's complement and we would add this number to the one stored in accumulator, that is 3fh. So let us write 3f in binary. So this is 3, this is f, and we would now write 2 and 3. And we add these two numbers, we perform binary addition, and at the end what we have is carry 1 from D7 output. But we invert the carry bit in the end. So this carry equal to 1 would be inverted and become carry equal to 0. So here there comes a 0. So there is no carry out from D7. Let's check the number of zeros, 1, 2, 3, 4, 5. It is odd, so parity flag is 1. There is also no carry from D3 to D4. So that is why auxiliary carry 0. Let us check this using Keil. So here I pasted my code and let us see what's the result. So I added another new item and added subtract file and put the code. Now I will build. 0 errors. And let's go to debug. I will step one line at a time. You can see that 3f gets stored in the accumulator and 23 gets stored in R3 register. Next you can see the parity flag changed to 1 and the final operation as soon as we move to sub B, subtract with borrow, the accumulator got the result 1c and parity flag changed to 1. So after this, even if it press this button, nothing happens. So we can say that our result, whatever we verified theoretically, was correct. Now let us see how we perform multiplication of two unsigned numbers. So we have byte by byte multiplication and command called mul AB is used, where one operand is stored in A register, that is accumulator register, and another operand is stored in B register. The result is a 16-bit data, and the lower 8 bytes are stored in accumulator and upper 8 bytes are stored in B register. So this is the program RG0H. Store 25H in accumulator, store 65H in B register, multiply both of them. So we first need to convert both of them into binary and then perform normal binary multiplication and add. And the result is a 16-bit data. The lower 8 bytes would be 99H and stored in A, and the upper 8 bytes would be stored in B. So this is the result. Let us check if this is true. Coming to the multiplication operation, we have two operands, namely 25H in accumulator and 65H in B register. Let's debug the code. You can see 25 got stored in accumulator, 65 got stored in B register. And in this operation, after multiplication, A has 99H and B has 0EH, same as this. So yeah, we can say that the operation performed is correct. Now let us see how will we perform the division of two unsigned numbers. So we have a command called div AB, that means divide A by B. And here is the program. So first we store 95 in accumulator and 10 in B register. Then we perform division AB, and A09A accumulator will hold the quotient and B register would hold the remainder. So here is the output, and now let us check if this is true. So here we are at Keil and I pasted my program over here. Now let us check if this is true. So we first build target. We have 0 errors and 0 warnings. Let's debug. Now we would step one line. You can see 5 are stored in accumulator register, which is equivalent to 95. 0 is stored in B register, Now you can see that question A is 09H, this should be H, and remainder is 05H. So our program is correct. For signed numbers, 8051 indicates an error by raising the overflow flag 1. So when we add two signed numbers, it is possible that result might be larger than capacity of accumulator to hold data. So maybe it could be more than 16 bits or more than 8 bits. So it is not possible to for accumulator to hold the data properly. So suppose if we have a number minus 128 in accumulator and minus 2 in register R4, we would add both of them. So let's write 128 in binary form. So this 128 could be written as minus 128 could be written as this in binary number. So you could check out how to find out binary for negative numbers. Minus 2 is written in such a way. When we convert it to hex, we would get APH, and in R4 we have FEH. And if we sum both of them up, we would have the result 126H, which could be written as 7EH in hex. So this is what we calculated, what CPU calculated. Now let us see how we as humans would perceive this. So when we look at minus 128 and minus 2 and subtract and add both of them, the result should be minus 130. But we are seeing that this plus 126, which was calculated by CPU, and the actual, which we know, are not equal. These both are not equal. So in such a case, overflow flag raises to 1. And after performing this whole operation, the output would be 0xFE in R4, in accumulator 0x7E. Here, final result in accumulator. Yeah. Similarly, in another case, when we have minus 2 in accumulator and minus 5, which is comparatively small numbers than these two. So we would convert them both to binary and add both of them. What we observe that the resultant, binary resultant, comes out to be minus 7, which is F9H. And if we go to actual, how we as humans perceive this, so we then also have minus 7 as the answer. So both of the results are same. Both CPU and actual output is minus 7. So in such a case, overflow flag is 0, meaning the result could be stored in accumulator and is within its range. And yeah, so your auxiliary carry is 1, and R4 register has FBH as output and accumulator as F9H. I pasted my addition of signed number code, and I have two numbers minus 128 and minus 2. So let us build target 0 error 0 1. Now debug. You can see APH got stored in accumulator, and next FEH got stored in register R4. Then we will add both of them. You can see accumulator after addition has final result in 7EH. Now let's take the PSW register, which has value 0 at 4. So here overflow flag is 1 because the actual data and accumulator data is not same, and carry flag is also 1. Now I have another two numbers minus 1 minus 5 stored in accumulator and register R4 respectively. Let us build target 0 error 0 1, then now debug. You can see FE got stored in accumulator and FB got stored in register R4. Next, after addition, F9 gets stored in accumulator as result. And if you observe the PSW register, which has value C0, we can see that auxiliary carry is 1 and carry flag is also 1. And here overflow flag is 0. Why this overflow flag is 0? Because the CPU output minus 7 and the real output, actual output, both are same. So we could say that the overflow flag is a 0 and accumulator is able to hold the data, hold the result. Thank you for listening patiently. You could also follow me on my two Instagram accounts, the Techie Diva and the Techie Guys.